We're very rapidly reaching the point where these quantum computers outperform classical ones, and that unlocks, or starts to unlock, all of the really exciting first applications of these systems.
7 years ago, when we started this series, things were very different. Scientists were still figuring out how to build quantum computers. But before we look at where we are now, we need to recap on one thing that hasn't changed: the basics of quantum mechanics, which my colleague Shinichi Samara explained.
When it comes to describing the universe, there's the physics of the very large, of stars, of planets and galaxies and their gravitational relationships. And then there's the physics of the very small, known as quantum physics or quantum mechanics. So before we do our next story on quantum computers, we need to do a little primer. But I warn you, things are going to get really weird. According to quantum physics, things can be in two different places at the same time. This phenomenon is called superposition and can actually be observed in the laboratory, where single atoms or subatomic particles can be shown to be in two separate places at once. For more than 100 years, Einstein and other physicists have been trying to disprove quantum physics because, well, it's just too weird. It simply doesn't agree with what we can see and experience. Einstein called it spooky. Professor Winfried Hensinger is a scientist who embraces this quantum weirdness, asking instead, how can we use these strange properties of the universe? So what was your inspiration for getting into quantum physics?
So it all started with a theoretical physicist named Gerard Milburn, who had this theory that he could make an atom move forward and backward simultaneously. So that is a possibility in quantum physics. And so what we did is we prepared an experiment. We prepared individual atoms. We made them move both forward and backward simultaneously.
But that's just so counterintuitive, so weird. Am I just not getting it, or is this really difficult to understand?
It is counterintuitive because we cannot see these things in the way we can prepare them in the experiment. And in order to understand something, you have to relate that to your personal background. And quantum physics doesn't really happen on a macroscopic scale. You can only observe it really well on a very small scale, on the scales of individual atoms.
Currently, the most challenging use of the quantum properties of the universe is in the building of quantum computers.
So the way how conventional computers become faster and add more and more transistors into the microchip. However, as components, transistors, are becoming smaller and smaller, it becomes more and more difficult to shrink them further. That's when conventional computers can't really become much faster anymore. Quantum computers are entirely different technology. There's nothing like conventional computers. They're relying on the strange phenomena of quantum physics. But rather than just looking at these phenomena, we're trying to tame them in order to build a machine that is now capable of solving certain problems where even the fastest supercomputer in the world would take billions of years to calculate.
That's a whole class of problems that contain many unknown variables, such as cancer treatments, forecasting weather and climate change, online security, both for generating security and breaking encryptions, optimizing traffic flows, predicting financial markets, and even gaming. So what's the difference between conventional computing and quantum computing?
So quantum computers make use of quantum physics, and as such, rather than encoding information as a string of zeros and ones, as classical bits, they encode the information as a string of quantum bits. And a quantum bit can be 0 and 1 at the same time. So what does that mean? Imagine you have the world's worst memory stick. A memory stick with only 2 bits, right? So imagine, for example, you write 0, 1 into your memory stick. Now your memory stick is full. It's done. Now imagine you have a quantum memory stick with 2 bits instead. In 2 quantum bits, I can simultaneously write in 2 quantum bits 0, 0, 0, 1, 1, 0, and 1, 1, and that all at the same time. Now that doesn't really sound that impressive. So imagine, for example, you have a memory stick with 100 bits. I can write in 100-bit number into my memory stick. But in a quantum memory stick, so if I have 100 quantum bits, now that's the number of different numbers I can encode into this quantum memory stick. So you can see how massively large the number of different numbers is I can encode into these just 100 quantum bits.
Today, the mysteries of quantum physics are being harnessed to create working computers, and a new race is unfolding to achieve quantum advantage, the moment when quantum computers outperform classical computers across a range of real-world tasks. Dr. Richard Murray is a co-founder of ORCA Computing, a startup that is pioneering photonic quantum computers, machines that use light to process information. It was 7 years ago I was involved in a film about quantum computers. Now, nobody was putting them in boxes and shipping them away to other countries at that stage. They were still things on a scientific workbench.
Yeah, exactly. And actually across the world, ORCA and other companies, we're investing in bringing these systems to market. We're investing in integrating them within classical computers, because one of the first applications will be, you've got an existing classical computer, you've got a quantum computer which isn't big enough to do everything you want, but if you put that side by side with the classical, you can do more. So we're investing a lot in deploying these systems, putting them side by side with classical computers, and then actually identifying the first applications. In our case, we spend a lot of time applying our quantum systems to AI, generative AI models, which we think is one of the first applications. So, I mean, frankly, it is amazing. As a field of physics that has existed for 100 years, only now has the technology been ready to be invested in, to be a commercial thing. And actually that investment is coming, and no surprise that the progress is happening. Companies are launching products, scaling up the systems very, very quickly, and also developing the applications alongside them.
What gets me is, with the brain we've got, we can't understand this quantum states, quantum world, but you guys are able to harness it and make it work.
So when you create a quantum state and then you measure it, it is a fundamentally probabilistic thing. And certain physicists had real problems with that. They thought that we just don't know enough. If we study the system more, if we learn about what's going on, we'll be able to interpret what's going to happen, deterministically. But that's not the case. It's a totally probabilistic law where you cannot, by definition, know what's going to come out of it. But saying that, that's not to say that we can't study this thing. Everything is boiled down to certain building blocks, which we know how to build. And we know the inputs and outputs. But when I say that we know the outputs, some of those outputs might be a probability. So we sort of summarize all of this in certain, sort of quite easy to understand operations. We generate single photons. We then create superposition states, so quantum states with those photons. We can mathematically describe those states really accurately. It's not to say we understand what they are, but we know how they work and like how they behave. So we sort of boil it down to, maybe you might call it like a practical level of knowing the key ingredients that we need and how to perform operations on those key ingredients.
Let me unpack one of the things you said. What's a photon?
A single particle of light. So every source of light contains these fundamental things, objects if you like, called photons. So there are you have electrons describe electricity, light is described by single particles called photons.
Can I say that that's the smallest indivisible measurement of light?
Correct, yeah, exactly. And there are trillions of them. So any light bulb will be producing literally 1 trillion photons every second. And we've been bombarded by these particles all the time. What we do is we make single photons which operate in a quantum way. So but they're essentially just the particles of light that we see all around us.
The fact that you can isolate individual photons, let alone manipulate those fundamental particles to build a quantum computer, that's already blowing my mind. What's the advantage in using photons?
There are a few different advantages, and by the way, there's loads of pros and cons. One of the biggest advantages is that these photons operate at room temperature and at room pressure. It doesn't need to be contained in vacuum, it just can be optical fibre. And so a lot of the advantages of our system is that it operates at room temperature, and pretty straightforwardly. So we can install our systems quite easily. We're using a lot of off-the-shelf telecoms components. So there's a lot of practicality, I think, that comes with photonics. I think everything else is a little bit more subtle, but just as powerful.
There are several ways to create the qubits used for quantum computing. Photonic quantum computers promise speed and scalability, and it starts with isolating a single photon of light. Richard, what have we got here?
So this is one of the core components of our system. So you'll find one of these in every single one of the ORCA system. It's the small module that makes our single photons.
Right.
Inside of here, you get laser light come in, and the trillions of photons that are contained within laser light are converted into just single photons.
Coming in through this blue fibre optic cable.
That's right. Fibre optic just channels the laser light into the module. Under this little hood is a piece of material that converts one photon from the stream of photons in the laser to just a single photon, a single particle of light.
So what is under this piece? It looks almost solid, but I see that there's screws in the top.
I mean, under here you'll see a piece of material that's no longer than a centimetre, and it's just the specific properties, crystalline properties, that just convert the frequency of light. The material itself is quite advanced, but it's pretty commonplace in research communities. There is a lot of just making sure it's the right length and it's got the right sort of optical properties so that it does exactly what we need to do to make these identical, perfect photons.
If I asked you to explain how it takes off a single photon like a farmer taking off sheep,
Yeah.
would you be able to explain it to me in a way I could understand?
So it converts the frequency, the colour of the light.
Oh, right.
So you'll take one photon that is blue and it'll be surrounded by trillions of photons that are also blue, and it just converts that one blue photon into two red photons. So you can do that because, you know, conservation of energy. The two red photons have the same energy as one blue photon, but because you get just two, you can tune that process so that it just generates just those pairs at a time. And then the reason we want two is, I mean, there's no way of avoiding it, but you actually measure one of the photons to give you a little signal to tell you that you have measured the photon.
Mind blowing. Mind officially blown again. The exact makeup of the crystal is commercially sensitive and is the result of 30 years worth of research spanning back to the University of Oxford. And how big was that when you started trying to build it?
Originally big, I mean the size of maybe one of these tables,
right.
And then this is probably the fourth or fifth generation. First generation was a bit smaller, shoebox size, and then even smaller. And actually where we're headed is to do a lot of this work on a semiconductor chip. So the future looks like shrinking it down even further to sort of chip-based size.
Wow.
This is an illustration of what we could do. This actually doesn't perform the same
So
operation.
all of that would be that?
Yeah, in fact you'd be able to do many of these on one of these chips.
Many?
Yeah, because actually what's important here is just under this hood. The rest is just optics and alignment and the rest of it. So you could have many, many of these devices on a single chip in the future. But our philosophy is just walk before you can run. These devices are hard to make well, you know, as we do, and then we'll do this well and incorporate it into our product, and then the next generation will look like this.
The ORCA quantum computers are built in their on-site lab before being shipped to customers around the world. So, heart of the beast?
Absolutely, yeah. This is where we build quantum computers. And you can see right here in front of you one of our PT1 and our PT2 system. So first and second generation quantum computers.
I have to be honest, it's not as science fiction-y as I thought it was going to be.
Good, yeah. We deliberately design our systems to look practical. Maybe I would even go as far as to say boring as possible.
Yeah.
Because that's what people in data centers want to see.
Right.
They don't want to see big, expensive equipment. They want to see practical systems that can be installed easily.
But, you know, when I see some of these other computers, they look very much like they're from a mad scientist movie.
Yeah.
Some quantum computers.
Yeah, so our benefit is that because we're using photonics, these photons, everything inside of here happens at room temperature. So the photons themselves are just carried in optical fibre. So in here you have a lot of leading telecoms, but it's just telecoms optical fiber type devices. And the good thing is that everything can be packaged up very, very conveniently, very practically inside of these rack-based systems that we use.
So what are we seeing?
So this is our system.
Yeah.
So you'll see that it consists of various different modules, and each of those modules carries out a different function. So the first module is used to create our single photons. This is where our single units of light occur. The next three modules we call the processor modules. These are where actually a lot of the quantum magic happens. These are where our quantum states, our superposition states are created, then they're manipulated, and then they come out. So by the time it reaches down here, the photons are measured. And measurement in quantum performs something quite strange. It has the effect of reading out, telling you where the photons have appeared, but it destroys all of the quantumness. So you can't measure your photons, but at the same time preserve any of the quantum stuff that's happening. So you do destroy the quantum state in the process of measuring it.
I say it again, it's just all too weird.
Yeah, exactly. But maybe we shouldn't know what's going on inside the box.
This weirdness occurs because of what's known as the Heisenberg uncertainty principle. In the everyday world, knowing where something is and how fast it's moving is simple. But at the quantum level, that all changes. The more precisely you know a particle's position, the less precisely you can know its momentum. Why? Because quantum particles like electrons and photons behave like waves. A spread out wave has a clear frequency, so its momentum is known, but it has no fixed location. Compress it to a point and the frequency becomes undefined. You can't have both. Now it gets even weirder. Before measurement, a particle has no definite position. It exists in multiple possible positions all at once, in a kind of cloud of probabilities. The moment you measure the particle's position or momentum, that collapses. To observe a particle, you have to interact with it, bouncing light off it, for example. That interaction forces one outcome. All other possibilities disappear. We've got Einstein and Newton, right, describing the very big. So we can tell at any given time where Jupiter is or where we are. Yeah. But when we go down to this less than microscopic level, this, quantum level,
yeah,
it's all just probability. We can't say where any given particle is at any given time.
Exactly. It's a real contradiction between the big and the small. And when you get into the details of the smallest length scales, things don't look like hard blocks anymore. I mean, people at school learn that you have these hard billiard balls,
yes,
these hard things,
yes,
protons, neutrons, and they circle around each other. Everything looks quite straightforward. They look like planets.
Yes.
The problem is that reality is that those things, in the laws of quantum mechanics, they're not hard objects. Right. They are probability distributions. They're chances of those protons, neutrons, electrons appearing in certain places. So they're not in one place at one time. They're smeared out, if you like, as a wave, and that's what gives us our understanding of atoms. And then take by extension the way we build quantum computers, these things called photons, particles of light. You can think of them like hard thing, laser light or lights around us stream us, bombard us with these particles, but actually they're also quantum things where those particles are smeared out. In our system, they can take multiple paths. So these indivisible particles can be split, they can be routed in different ways through networks and recombined with themselves and things like this. So you'll notice that there's this really weird contradiction, and I think quantum is full of contradictions. You can't really describe it very well. And in fact, the best way to describe it is just with maths.
So we just don't worry about the complete contradiction to what we see in our everyday lives?
Not in our day-to-day. No, I mean, it's fascinating, right? I mean, we're all excited by what might be going on behind the scenes. But yeah, at a practical day-to-day level, you don't need to know that stuff. I guess you just live with the uncertainty. If you accept these are the ways that these things operate, what can we do with it? And it turns out that you can actually do quite a lot with that understanding in all of the different applications of quantum in the areas of building new computers, new sensors, new communications. We can do all that stuff without really knowing or keeping ourselves up at night with the details about what's going on. And then what's amazing is this whole system operates very, very quickly. We run through those operations many, many times. And then the client would then have one of these systems next to their existing computing servers.
A classical computer.
Classical computers. So our customers install them side by side with their classical computers, and this whole system hands over quantum to classical, back to quantum, and it's part of the overall workflow that our customers run.
So they're kind of running in parallel.
They're running in parallel. The nice way to think about it is using the quantum system as an accelerator. So it's a side-by-side operation. It's part of the workload which is being run because the quantum system is better for certain parts of that workload.
We've found out that analogies don't work with quantum, but it's like a turbocharger.
Yeah, exactly. That part is fine. I mean, the world of computing is used to incorporating different technologies to turbocharge the calculation they're trying to run. I mean, 20 years ago they introduced GPUs, and now NVIDIA and GPUs are everywhere. Yeah. This is the newest sort of generation, if you like, of accelerator turbochargers for some of the most exciting workloads that our customers are interested in.
Quantum computers will be used to solve complex, multi-dimensional problems beyond the capacity of classical supercomputers. So far, ORCA have delivered their systems to several high-profile government and research institutions exploring applications in areas such as energy, healthcare, logistics, manufacturing, and one area with huge potential, chemistry.
I mean, you might ask sort of how do you take advantage of all this computational complexity, but within the constraints that come with the fact that there's a quantum system. So it's often described that the number of inputs to a quantum system is quite small, and the number of outputs is quite small. But in the middle, there'll be lots and lots of different permutations, combinations that are assessed. And so one of the most exciting areas, I think, is in the sort of search for new molecules that come from the existing ingredients that we have, but have never been actually computationally assessed. Because to run all of these simulations of different protein folding algorithms, here's a number of different carbon atoms, how do they structure themselves, actually is reliant upon all of those different atoms sort of interacting with each other. And I don't know if that sounds, but it's actually a huge computational task to give you the exact solution. And therefore what that means is actually there are loads of therapies which we might have, and it is as bold as saying cures for cancer, completely new forms of therapy, which we have no idea about because they don't occur in nature.
We recently visited the UK's most powerful classical supercomputer, Heisenberg AI, at the Bristol Centre for Supercomputing Research. Researchers there are already using AI to study complex protein structures.
A typical protein will be something like, the smallest is something, they can be very small, like 30 amino acids, and the biggest is like 20,000 amino acids, and a typical protein is, a couple of hundred amino acids. But you have lots of copies of those proteins, so you might have like thousands of a copy of an individual protein in an individual cell. So yeah, there's like, and each of those proteins is interacting with lots of other proteins. The complexity kind of mounts and mounts.
Yeah. Using cryo-electron microscopy to take high-resolution images of proteins, they are then using algorithms to restructure these images into a high-resolution 3D model. Being able to capture large-scale and detailed images means one thing: more data.
One session on the microscope, we can end up with terabytes of data. So it's huge amounts of image data. So that gives us a large task for a computer to churn through and to go from those two-dimensional images to our 3D models and reconstruction. We can augment our modelling with these predictions. We have known data and the predicted structures, and we put them into our experimental data. So it's a combination, but it basically accelerates many steps.
The latest supercomputers running AI are already making huge breakthroughs, and when combined with quantum, they could be even more powerful. In a recent milestone, scientists at Cleveland Clinic and Riken used 2 IBM quantum computers and 2 supercomputers to model a 12,635 atom protein, the largest known to be simulated by a quantum computer. ORCA Computing is partnering with the Technical University of Denmark to develop hybrid quantum AI solutions to accelerate biomanufacturing research.
So quantum systems are really, really good at modelling nature because nature is quantum. And the examples keep coming from there. If you look at how plants harness sunlight to produce food, photosynthesis, you think you know it, you learn it at school. We as humans have no idea how plants can be so efficient. We have no idea how chlorophyll, the sort of molecule that harnesses sunlight, how it can be so efficient. So if we can model that, and that's a quantum process, we as humans could have much better ways of converting sunlight into food and energy. Wouldn't that be great? High temperature superconductors, no idea how they work. Hemoglobin, our blood, no idea how they work. So each of these is like a molecule, a quantum molecule, which we think we should know about because we're pretty advanced being humans. But we have no tools and we don't have the understanding to actually help us understand how we can copy these molecules and put them into sort of useful production in society.
So in effect, these could be so flexible, they might end up solving problems that we're not even thinking about at the moment.
Oh, 100%. I mean, essentially we are providing new tools, the power and the performance of which has never been seen before. So in 20, 50, 100 years' time, who knows what the applications of these completely new types of computers are.
With so much potential, nations around the world are keen not to miss out on having their own quantum systems and are investing heavily. In the UK, £2.5 billion was set aside. China is also a major player in the quantum field, with substantial public investment and long-term strategic planning. Quantum Origin, a Hefei-based company, recently unveiled their latest quantum computer, the Origin Wukong 180, which boasts 180 qubits. The computer reflects continued progress in China's development of 100+ qubit superconducting systems. Superconducting qubits, which require specialised cryogenic environments, are one of the most mature methods of building quantum computers. These sci-fi looking machines are also used by the likes of IBM and Google. So the promise of quantum is approaching rapidly, but how soon will we see the real-world benefits of this technology?
This is really probably the hottest question in the industry. When will these things be useful? I think it's certain that applications will exist once we reach a certain size. Those systems will be available at the end of the decade, but right now we're at the point where we don't quite have as much performance, we don't quite have the quantum computers you need to run all of the algorithms. But we are finding that you can run certain algorithms, and in there lies a lot of the potential, like bringing forward the point where you can make quantum computers useful. So it's really on the cusp of a breakthrough, really being rolled out into day-to-day computing tasks and these types of things. We have only started to uncover the future power of computers in general, modelling materials that we see in nature and producing new materials and systems that we have yet to even think about, let alone actually use. So the future for me looks a lot like maybe not noticing the impact that quantum computing has, but certainly noticing new drugs, new materials, and a fundamentally different way of life underpinned by a completely new paradigm of computing.